Hello and welcome to lecture 61 on the properties of sine and cosine. We have defined all 6 trigonometric functions, but we're going to start with sine and cosine. So now that the sine of x and the cosine of x have been defined for x in R, for a real number, we would like to look at the graph. But before we look at the graph of these two functions, we want to figure out some of their properties, okay? And in terms, looking at the property will give us an easy way to understand the graph. The first of these properties will be the domain. This is always what you do when you look at a function. The first thing that you want to know is, where is the function defined? So to look at the domain of sine and cosine, of course, we have to look at the definition of sine and cosine. How is it defined? And the definition is not completely straightforward, right? You have to take a point. Given an x, if you're given x in R, you have to find this x somewhere on this axis. So that's easy, okay? So suppose x, here, let's take a negative x right here, okay? It would be negative. Then what do you do after that? You wind the axis around the circle. So suppose my x goes right here. Let's take it right there. Okay. Then after that, you figure out the x coordinate of the point and the y coordinate of the point. This is how you will get the cosine of x right here, and there you will find the sine of x. Okay. This is how you define cosine and sine. So the question is there any real number on this axis that you can't wind? Okay, is there any position right here that cannot be wound up, like 0? Can you wind 0? Sure, it's gonna stay right here, right? It's not moving. Any value in the positive direction can be wound up. Maybe you're gonna have to turn many times around. It's okay, you can still wind it. Okay, likewise in the negative direction you can wind any value, even if it's negative. Okay, so this is the first property. The domain of sine is the same as the domain of cosine, and it is all real number. All right, first of all. Second, let me get rid of all this winding here. Let's look at the range. What is the cosine? Here, let's start with cosine. What is a cosine of a real number? It's the x. It's an x coordinate. It's an x coordinate of the point on the unit circle. So here are some points on the unit circle, and you can see that the x coordinate is right here, right? And so the range is between -1 and 1. What about sine? Sine is a y coordinate. The y coordinate is right here. You cannot go past 1. You cannot go past -1. So the range for sine and cosine is all between -1 and 1. Okay, so the range of sine is the same as the range of cosine, and it is -1 and 1. So you need to know that. This is very, very important. All right, the next property is about the parity. Do you remember what it means? Parity? Parity means odd or even. Okay? So this is an interesting case right here. So again, I need my winding function. So here's my unit circle. Here's the y-axis, the x-axis right here. And let's wind. Let's take a real number x and let's wind it. So parity. You want to figure out if something happens to the negative sign inside cosine negative x, or to the negative sign inside sine negative x. If something happens to it, then you can say something about the parity. If nothing happens, if you don't detect anything, then it's neither odd nor even. Okay, so let's take an x right here. Here, I'll take an x right there. Okay, this x right here. And because I'm looking at cosine of negative x and sine of negative x, I also need to be taking the opposite of x. So I'm going the opposite direction right here, same distance but on the opposite side, and I'm taking negative x. All right, let's wind x. So suppose x winds there and end up right here, x right here. Okay, this is an arc of length x. And let's wind negative x. So negative x in turn would be somewhere here, right? And this would be negative x. Now, the length of this arc, as the absolute value of the length, if you want, is going to be the same, okay? Therefore, we have some kind of symmetry here at work. This point should be symmetrical with respect to the x-axis. And so what does it mean? It means that, what is this one right here? This is the cosine of x. And what is this one on this? This is the cosine of x right here. What is this one on this side? This is the cosine of the opposite of x. And so we have that the cosine of negative x is the same as the cosine of x, right? That's the first one. How about sine x and sine negative x? Well, where's sine x? It is right here, sine x, right? Where's the sine of negative x? It is right there. And again, for obvious symmetrical reason, this right here is the same distance as that, except that they have opposite sign. So the sine of negative x should be equal to the opposite of sine x, right? And so right here we say that cosine is even, okay? If a function swallow up the negative sign, it is an even function. Right here, sine is odd. Sine is odd. If the function, like if you want, spits the negative sign outside, it is odd. Okay, I'm sorry for the image. All right. Now, for the next property, we need to look at a new definition that we haven't seen so far. And this definition is a definition of periodicity. All right. So let's try to understand what the periodic function is. I have a graph right here to show you what it is. Periodicity. We're going to be looking at periodic function. So in my notes, please check on my notes, I give two definitions. And the first one is very informal. It's a graphical definition. A periodic function is a function that has a repeating pattern. When you look at this graph right here, you can see a repeating pattern. For example, here, I'll start right here at this point, and I'll try to stop once I have my full pattern, right? So, not there. Keep on going. Is that a pattern right here? No, not here. And I think that should do it, right? This is my repeating pattern, because all along you just repeat this forever right here, and then you have another one, right? And it goes on forever. So this is called a periodic function. And the pattern doesn't have to be this one, okay? The pattern can be anything you want. Here, I'll start this time. I'm going to start right here. Why not? Here, I'll start right there. I'll start right there. Where is my repeating pattern? So I'm doing this right here, and then I'll stop. Should I stop here? No, I don't have a pattern if I stop here. I need to go further. I need to go right here. Here is my repeating pattern. You want to see? Check out the second pattern right here. We call that a cycle. This is a cycle of the function, okay? Let me draw a second cycle right here. And right here, that's a second cycle, right? It's the same pattern, but a little bit further on the x-axis, right here, and another one right there. Okay, so you just repeat a pattern. Okay, now let's define a couple of things. So let me erase that again, and I'm gonna take an easier pattern. It doesn't have to be an easy one. Okay, here I'll take this one right here. I haven't looked at this one. For what I want to define, it's going to make things a little bit easy right here. And stop. Let me get a second one. And stop. Okay, all right. I'm going to define the period. The notation for period is t, okay? And this is what we call the period. And the period is a length, okay? The period is an x length, the x length, sorry, of a cycle. It's the x length of a cycle. So for example, look, if you go from here to here, that right here, this distance measures one period. Of course, you can take it from here to here. We saw that a cycle, you know, it doesn't have a definite shape. It can be this one right here, but it can be another one. This also measures the cycle. And if I start my function, like for example right here, let me see, let me not make a mistake, it would end up right here. Okay, so all of these of course are the same length. Okay, this is called a period, a periodic, and we say we have a periodic function. All right, and the last thing I want to say, so this is the graphical definition. Let's talk about the analytical definition now, so you have all of the drawing in my notes. Okay, the analytical definition is also interesting. It says basically that if you take an x, let me take for example this x right here, x, and let me take, this is f of x, right? So f of x is right here, x f of x. Then if you move right here on the x-axis by one period, right here, so I know I'm going to be about here. If I move by one period on my x-axis, this way, for example, right here about, okay? So this is x plus t. What is the output at x plus t? It's going to be the same as the output at x. Let's move another period, so that's going to be now x plus 2t, right? Here, that's 1t right here, right? From here to there. And I'm adding another t from here to here. So this is x plus 2t. What is the output at x plus 2t? It's going to be exactly the same as the output at x, because we're moving by one full period. And of course, it would be true if you move another period right here, and you check out the output at x plus 3t, and then you would have the same value right there. Okay, now of course, if you start with another x, the output will be different. Okay, if you start, for example, here, let's take this x right there. If you start with this x, the output is right here. Okay, so let's call it x1. This is going to be f of x1. Okay, and f of x1 is not f of x. That's not what I'm saying. I'm saying that if from an x you move by exactly one period right here, another period right there, you will find the same output of the function. Okay, if you move another period right here, you will find the same output. Okay, so this is a second definition. It says that a function is periodic if there is a t in R such that f of x plus t is equal to f of x for any x in the domain of the function. Okay, so this is a much more analytical definition of a periodic function. Okay, let's do some example now. So in the first series of example, I want to determine the range of the function. So I know that the range over my regular sine and cosine is -1 from -1 to 1. So let me look at this one right here. So we have a couple of graph shifting happening, right? So you got y equals sine x, and the range is -1, 1. What happens to y equals sine x if you go to y equals 3 times sine x? So the range will become -3, 3, right? That's a vertical dilation. And then what happens from there when you go to 3 sine x minus 2? Then now you shift everything down by 2, so it is -5, 1. That's the range of my function. I'm going to let you look at the second one right here. It should be pretty straightforward. Let me look at 3 or 4. I'll do 3. So here again, I start with y equals sine x. Now, we don't really have a result for squaring, right? What happens when you square? But this should be pretty straightforward. When you square everything, what's going to happen is that there won't be any negative things, right? So the lowest value, and sine 0 is 0, so the lowest value is 0. And what's going to be the highest value? If you square any number between 1 and -1, the highest value you're going to get is 1, okay? So this is what's going to happen if you square the function. And from there, you multiply by -2. So be careful, don't forget here, you got two things going on, right? The first one is you multiply by 2, right here. And the second one, you multiply by -1. -1 is a reflection across the x-axis, okay? Reflection, sorry, I said across x and I meant across x. Reflection across x-axis, y-x, y becomes negative y, right? Y right here becomes negative y. So that becomes now negative 2, 0. Don't forget you gotta switch the order. And then we add 5. So if you add 5, you'll be at 3, 5. This is the range of this function right here. So I'll let you do number 2 and number 4. Let me see for other examples. Okay, so what about this one? I'm gonna do number 6. I'll let you do number 5, and I'll also let you do number 7. So what do you do? Simplify cosine x plus cosine negative x. Well, cosine x is cosine x, there's nothing to do. Cosine negative x, cosine is even, so cosine negative x is the same as cosine x, so it is simply 2 cosine x, okay? So the expression I gave you is just 2 cosine x, very straightforward, nothing difficult. Please do 5 and 7. Let me look for another problem. Oh, I realize I talked about the periodicity, but I haven't looked at the period of sine and cosine, which I need to do, and then we'll get to the end of it. Okay, so actually I would like you to do number 8, so I'm not going to do this one. So let me talk about the periodicity of sine and cosine, and that will be the end of the lesson. So let's study the periodicity of sine and cosine. So for this, I'm going to take a real number on this tangent axis right here. Okay, so let me take a little bit larger, you'll see why. Here I'm going to take an x like right here, x right here, this is x. And then to this x, I'm going to add 2 pi. So I'm not sure where that's going to be, suppose it is like right here, okay? This, I'm adding 2 pi right here, this is 2 pi. And this point is x plus 2 pi. Okay? Let's wind. So when you wind, you see this x is going to drop right here about, right? This is where my x is. It's going to drop there. And so right here you have the cosine of x. And here you have the sine of x, right? Now, anyway, what's going on if you want to figure out the cosine and the sine of this point? Well, at this point, look, you've winded this right here, but you still have some length to wind right before you get to x plus 2 pi. So you still need to keep on winding. But what do you need to wind? You need to wind a length of 2 pi. This is 2 pi. But what is the circumference of the circle? 2 pi r, and r is 1. So it is 2 pi. So this x plus 2 pi is going to be at the same places as x. They're going to fall at the same spot on the unit circle. Therefore, the cosine of x plus 2 pi is the same as the cosine of x. And the sine of x plus 2 pi is the same as the sine of x. Okay? So what do we say? We say that cosine and sine are periodic. These are periodic function, and their period is t is 2 pi. Okay, if you move by 2 pi, you're going to have the same output. By the way, what did we call that before we looked at real number? Okay, you know you had this formula right here. The trig of an angle is the same as the trig of the coterminal angle, right? Alpha coterminal. And what is a coterminal angle? It's alpha plus, it doesn't have to be 1 2 pi, it can be any 2 pi right here. And this was called the coterminal angle formula. We don't call it coterminal angle because we don't deal with angles. Okay? Alright, let's see the last series of examples and we'll call it a day. Okay, what's going on right here? You have to express sine of x plus 15 pi in function of sine x. So here's what I'm going to do. I'm going to take x plus 15 pi, and I'm going to get rid of my multiples of 2 pi. This is the same as sine of x plus pi plus 14 pi. Now 14 pi is 7 times 2 pi. But this is a period, right? So basically, you can just get rid of it. The output will be the same. So this is just a sine of x plus pi. Now, how do you simplify that? Well, let's take a look at it, okay? Let's take a look at it. Look, Here's the unit circle, x-axis, y-axis. Let's take an x. I'll take this x right here. Here's an x right there, okay? This is x, so therefore you have angle x right here, right? And let's add a pi to it. If you add a pi, you're going to be right there, okay? You're going to be right here, like that. So where's the sine of x? The sine of x is here. This is sine x, okay? But this is now, this length right here, the whole green length is x plus pi. So this right here is the sine of x plus pi. And by the way, we could look at the cosine too. This is a cosine of x plus pi, while this is the cosine of x. Cosine of x, okay? Now, for symmetric reason, like for example, we could, I'm saying symmetric reason and you think I'm fooling you right here, but this angle right here is congruent to this angle right there. This is 1, you have a right angle right here. I'm pretty sure we have angle side. Angle side, yeah, that's congruence theorem. So the two triangles are congruent, therefore this is congruent to that, and then this right here is congruent to that right there, okay? Therefore, what do we have? This is what I mean when I say for symmetric reason, okay? You have to look at the detail of some congruences here, but I don't want to get too detailed. What do we have? We have that the cosine of x plus pi is the opposite of cosine x. It was not the question that was asked, okay? The question that was asked was about sine. The sine of x plus pi, and the sine here, I'll write it here, and the sine of x plus pi is the opposite of sine x, right here. This is how you simplify the expression I gave you, okay? So please do number 10, and let me see. And you can do number 11. It should be very straightforward too. All right, that's about it. I just want to say just a quick word about these two properties that I haven't mentioned, okay? I recapitulated the property we've covered, and here I'm adding two properties that we're very familiar with. The first one, oops, that should be x's, not alpha, okay? It should be x's. The first one is really a duh, because what is sine and cosine? Sine and cosine are the x and y coordinate. This is cosine of x, and this is sine of x. Right here, the coordinate of this point. Where's x? Right here. Okay, x is right there, right here. Or you could also say it's right there. All right, same thing. The coordinate of the point of the unit circle, of course, by definition of the unit circle, cosine square plus sine square will be equal to 1. This one I haven't proved. The proof would be like the one that is in my note. I haven't gone over it. It's a bit technical and not that interesting. Thank you for watching.